Okay, Assalamu alaikum, Bismillah ar-Rahman ar-Rahim. In this lecture, inshallah, we will start by talking about the basic morphological operations. These were the parts that we didn't talk about last time. So basically, we're going to talk about these a little bit. We're going to talk about binary morphological operations, grayscale operations, and color operations. Usually, you talk about only binary and grayscale because the color is just is treated just like three grayscale images. So basically, it's like a generalization of the grayscale morphological operations. Then we're going to talk about the two-dimensional discrete Fourier transform theory and implementation in Matlab. And we're going to give many examples on that so that you can understand it. I need you to deeply understand discrete Fourier transformation because it's very important. It's a basic theoretical background that you need to have. So we're going to spend some time talking about it. If we have enough time, we will go into the first part of the assignment where we have samples from the K-space of MRI, which is the Fourier domain. We will learn that the Fourier domain of MRI images is called K-space, and basically this is the domain of a data collection. So basically the data that is measured, that are measured from MRI coils are basically samples from the Fourier domain. So we will learn how to, first of all, we'll learn how they look like, and then we will learn how to deal with them and basically reconstruct a sample MRI image from the real data that I gave you in the basic data that I gave you for this research problem. So basically I gave you some samples, like some data points, like this file right there, MRI K-space data. Basically, it looks like I actually made it to look like a text file so that you can see the samples, but usually it comes in a binary format. In any case, I'm going to give you the code that reads the K-space, and then we will look at it and basically discuss several aspects of it related to the periodicity assumption in space and spatial frequency. We'll talk about the magnitude and phase of the spectrum. We'll talk about the real and imaginary parts and whether they are critical or not. It's whether, if, for example, if we switch the data between the real and imaginary parts, basically take the real part and make it imaginary, and the other way around, make the imaginary as real, would it change anything in the image? Okay, so basically we discuss that from a practical point of view. Basically, we're going to experiment and do that ourselves, and then we will learn how this is actually theoretically, can be derived. We'll talk about sampling and resampling in the frequency domain, meaning that what is the meaning of sampling in the frequency domain? Because as I was saying a few minutes ago, basically in MRI, we measure the data in the frequency domain. So we cannot measure continuous data. We have to sample the data. How can we determine the conditions of sampling in the frequency domain so that we can get the right image? And how would resampling or improper sampling affect the resultant image? At the end, we're going to talk about two research problems. One of them is motion artifacts in MRI and partial Fourier imaging, where we reconstruct an image from only a part of the Fourier domain. These are active research problems, and they are very much related to the theory of Fourier transform. Okay? So do you have any questions about the topics? Okay. So we'll start with the morphological operations. So basically, morphological operations, basically we talked about, first of all, we talked about linear filtering. And we learned about it, basically, if we have an H that looks like, for example, something like this. Okay, you have here some numbers, okay, whatever these numbers are, okay, like whatever, A1, A2, A3, A4, A5, A6, A7, A8, A9. Okay, these are the kind of things that we saw before. We've called something like this kernel. And we learned that this is basically the H, the impulse response of a filter. And we have an image. Usually the image is much larger, basically something that looks like this. Let me draw it the proper way. It's a bit larger, basically. Okay, this is the image. Okay, it can be of any dimensions. Okay, you have, for example, N1 and N2, where N1 is the dimension, the size in dimension 1, and N2 in the size of dimension 2. And basically, the result of linear filtering is just a convolution between the image and this kernel. Okay, so we'd come up an image, another image, like what you did in your assignment, which you all did very well in, by the way. So basically, it's going to be another image, and this image is usually the same size as the original image. And basically, the values inside the resultant image, in the output image, usually are affected by the type of kernel that we used. Basically, these numbers change the output image depending on what they represent. For example, if we take something that looks like 1, 1, 1, 1, 1, 1, 1, 1, 1, okay? How do you expect the output to be? The output would be like what? You already did that in your assignment.
Average filter.
Average filter, right. This is an average filter, okay? So basically, if we end up with something like this, we use something like this, it would be an average filter, okay? Okay, so if you use something else that looks like this, and it's like, for example, -1, -1, -1, 0, 0, 0, 1, 1, 1. What would it do? So this is average. Yes, right. So this is average, and this is edge detection, okay? So depending on the kernel, basically we change the numbers here, and we do perform this convolution, and basically we end up with the output image, okay? And this convolution, by definition, the linear filter is called linear because the convolution is the linear operation. Okay, so basically linear means that if you have two images, if you have the linearity by definition implies superposition. Superposition means that first of all, additivity. Second of all, scaling. Meaning that if you have a system that is represented by H, okay, if you have, for example, X1 convolved with H is equal to Y1, and X2 convolved with H is Y2, if you input to the same system X1 plus X2, the output will be Y1 plus Y2. Okay, this is the additivity. Okay, this is additivity. This means that the system is additive. The second property, which is scaling, means that if you have X1 or X convolved with H is equal to Y, if I come here and instead of entering X, I'll enter alpha X. This alpha, since this is linear, will actually come up exactly the same way at the output. So this is the scaling property. Okay, so this defines a wide range of filters, and you can actually design the kernel to have any property you want, like what we talked about last time. We talked about the Laplacian, for example, so that we can detect the edges in all directions. We can talk about something like edge enhancement filters, things of that sort. So depending on the design of the filter itself, we can actually change the properties, but in all filters, the whole operation is linear. Okay? It's very important to start talking from linearity and the definition of linearity, because basically what we're going to talk about now is something that is nonlinear. So basically, the nonlinear filter is something that does not, basically, you cannot represent it with a convolution. Okay? So basically, let's start talking about the morphological operations as an example of nonlinear operation filters. Okay? This is nonlinear filter. It's exactly the same. You assume also that you have something that looks like the kernel, but here we're going to talk about it as just consider it exactly the same as 3 by 3, but actually it can take any shape. Here we're going to call it structuring element. Okay, sorry, let me just draw it. So this is equivalent almost to the kernel. Okay, the way you apply this kernel to the image is a little bit different. So for example, let me just draw something here. And let's start first of all, talk about binary morphological operations. Okay, so basically when you try to apply this kernel to this image, you're not going to do convolution. Basically, you put it here, for example, if I talk about as basically affecting these elements. Okay, if I talk about binary, if I talk about binary operations, or binary morphological operation, we will define an operation where we basically multiply the elements here by the elements here in the image. Each one of these elements by each one of these elements in the image. Let's call these images in the image, or these pixels in the image, let's just call them I, okay? And these elements in the structuring element, let's call them SE, structuring element I, okay? You basically multiply each one of these II times SEI, okay? And basically, instead of adding them together like we do in the convolution process, I'm going to basically list them as numbers, okay? So for example, I1, this is for example I1 here, and this is SE1, okay? So I'm going to list them as numbers I1, SE1, I2, SE2, and so on until here I capital N, SE capital N, where N is the size of this kernel or the size of this structuring element, okay? And instead of adding them together, I'm going to take these basically and basically apply a nonlinear operation on them. So basically I'll consider each one of these as a separate number and then apply a nonlinear operation on all of them. For example, the first process or the first type of morphological operations called erosion. Or basically you're doing eroding the image, okay? So Matlab, let me just write it as Matlab, basically, it's a function Matlab called erode, okay? Erosion means that basically you're gonna start or use an nonlinear operation here of minimum. I'm going to take the output of applying this kernel as the minimum of all these numbers. Okay? There's another operation called dilation. Basically, it's dilate. Dilate means expand. Okay? Here, I use another operation called the maximum. Okay? Let's try something like this and see how it looks like. Okay? Let's just assume that we have a binary image. Okay, let's just put a binary image here, like 1 0 1 1 0 1 1 1 0 0 1 1 1 1 1 1 0 1 0 1 1 0 0 1. Okay, and basically the kernel looks like this. Let's just assume it's ones. Okay. Let's try to compute the output of this. Okay, so we're going to use this and basically erode it with this particular kernel. So basically the operation will be like erode of this image, comma, this kernel. Okay. So when we do that, basically we're gonna take this and put it here in the first 3 by 3 and multiply these by these. Basically it's 1, so basically it's gonna be exactly this one here. Okay, it's exactly this one here, basically. Multiply these by these, exactly these same numbers, and take the minimum. What would be the result?
0.
Would be 0, right? Where do we put it? Usually you consider it here. Basically, it's basically considered as long as we put it here. Basically, we replace this part here, or basically compute the output at this center part here, okay, as the result that we got. If you want to get this element or that element, we will consider everything outside as zeros. So basically, if you do that, if you consider everything outside as zeros, so all the border elements here, if I put this kernel here, centered here, so it's going to be like that. As long as you have 1 0 in the kernel, the output will be 0. So basically, all the border, if you have here 6, all the border elements in the output will be zeros. And it's exactly the same, basically, for all the rows. Is it right? No, this is not there. Okay. So all the output here will be 0. Imagine that basically, in order for you to understand why that is, if I wanted to compute this, then I have to put a kernel here. And basically, this kernel will be zeros outside. As long as you have 1 0 and you're computing the minimum, then you will end up with what? With 0. So all the border elements in the output will be 0. This one here, which is what we computed here, will be 0, as we said. If you move to the next one, basically, if you have 1 0 inside the kernel, the output will be totally 0. Okay, so basically here you have a 0 here. If you stand here, you will have a 0 here. If you stand here, you will have also a 0. So basically it's going to be a 0. If you stand here, still you have this 0 and that 0. So basically it's going to be 0. If you come here, basically all the elements, basically if you put the kernel anywhere, you will find that there is a 0 somewhere, right? Right?
Yes, doctor.
Okay, so basically we'll end up with an image that looks all zeros.
1 0.
Okay? Doesn't seem like a useful operation, right? We made everything zeros, right? It doesn't seem like a very useful operation. Let's try also the, if we try the same, instead of erosion, we'll do the dilation. Dilation will be a little bit more useful because basically you're taking the maximum. So basically if you have 1 anywhere, you will get the maximum. So basically it's going to be 1. So basically if you stand here, you have 1. So basically it's going to have to be 1. So basically for the dilation, let me write it in another color so that you see it. For the dilation, the output will be for the border here. If I put the kernel here this way, so you have 1. So the first element will be 1. You have 0 if I stand here, 0, but there is the neighboring elements that are 1. So basically this will be also 1. This 1, 1, 1, 1. And also here 1, 1, 1. And here is going to be 1, 1, 1 also. And here you have 2 zeros, but actually you have 1 here and 1 there. So 1, 1, 1, 1 also. If you stand in the middle, basically you will find that basically if you do the dilation, you will have in any kernel, in any 3 by 3 kernel, you will have at least one pixel that is 1. So basically the output from the dilation will be 1 all the way. Okay, so basically it's going to give you something. Basically here it was all zeros, here it's all ones. So as I commented on the erosion, it doesn't seem like a very useful operation, right? So let's see example in Matlab where this can be very useful. Okay, so we'll start in Matlab. Maybe we'll have another code here. Okay, this one. Yes. Okay. So lec 5 codes.
Doctor,
Yes.
we didn't see that.
Okay, I'll change the sharing. Can you see it now?
Yes, doctor.
Okay, so we have lecture 5 code now. And basically, in order for us to see the effectiveness or something like this, let's do something like, I think there's one of the examples in the images that we saw in Matlab. Let's start with a binary image that we can understand a little bit more, image data here. Do you see a binary image? This is binary. This is right there, binary, right? Okay. You have here circles, right? Circles. Looks like this. Okay. Let's use this particular example. Okay. So what I'm going to do here is circles.png, right? Yes, right. So image is equal to image read of circles.png. And we're going to display it. Image show of image. That's it. Okay. Okay, it looks like this. Basically, a bunch of circles, and they are touching. Okay, they have basically they have a little bit of overlap here. So basically, they look like a certain, just like a one object. Okay, so imagine that you have a problem like this, and you're asked to count the number of coins or the number of circles here. Imagine that these are coins or they are circles, and you'd like to count the number of objects here in this image. How would you do that? Basically, if you try to consider each one of them as a separate entity, you cannot do that because actually it's basically merged with the other ones. So how about if we use something like erosion? Would it enable us to make these objects a little bit smaller so we can actually see the difference between them or not? Let's try that. So basically, what we're going to do is use first of all the function that creates the structuring element that we use in our morphological operation is strlen, which is structuring element. Okay, morphological structuring element. Okay, so we can decide how it looks like. So basically, it's very much like the one that we saw, a special that we saw in images. We can actually have all kinds of shapes. We can have it as a rectangle, and as a square, as a cube. If we have 3D even, we can make it as a diamond shape or a disc or whatever. Okay, let's choose it as a disc. Disc, you can basically choose the radius and basically the I'm not sure about the n actually, but let's see. For the circle or the disk, you specify the radius r, and n is the number of structuring elements used to approximate the disk shape. It's basically, it's not necessary. You can just make it 1 or just use the square one. Okay. So let's start with the square one. So I'll just say SE1. Just if you use another one, strlen of square. And let's see how the size of the image is. The size of the image 256 by 256. We can choose a size for the square to be, for example, 11. Okay, it's better to use it as, actually it doesn't matter. You can make it even or odd, it doesn't really matter. Okay, and basically we're going to do erosion. So basically there's a function called erode. Okay, so I think it probably can be here as a, yes, image dilate and image erode. Okay, in order for us to use image erode, we just write image erode of I, the image, and basically the structuring element. Okay, so we will say this image 1 is equal to image erode of image and SE1, the structuring element that we just saw. Okay, let's try to use several sizes. Maybe you can have another one with a size of, for example, 20 or 25 even. Okay, let's see what's the difference. Okay, and maybe we can just draw them all on the same figure. So it's probably better to just put them together in one figure like this. Okay. Image 1, image 2, image 3, and also we have border. Right, so that it fills the whole figure. Okay, another additional one. Okay, is it okay? Should be okay. Let's see what comes out of this. Okay. Okay, our recognize function image 3. Okay, image 3, we didn't change that. See now, basically, I think image 1 is shouldn't look like this. Maybe there's an error. Oh, okay, this should be image, just image. Oh, okay, sorry.
Please, Doctor.
Yes, go ahead.
Border and height. What was the meaning or what's the function of these two words?
The function of what?
What the functions of these two words? Border and height.
Basically, I'll show it to you with and without that. Okay. So just change that here. Image SE. Oh, okay. Here, SE2, SE3, and I have image 1, and image 2, image 3. I'll have another figure. Without that that thing that Reno commented about. Figure 2 without this. It's just instead of having a figure inside, it basically fills out the whole figure window. Let's see the difference between these. Image 1, image 2, image 3, it should work. See the difference between these two? Okay, here you don't have that wide border in the output. Okay, so it's much nicer actually. When you try to save this figure as an image, you will end up having this outside border. Okay, here you're just gonna get something that looks like this.
Yes.
Okay.
Thank you.
Okay. Now let's just look at this. Basically, this is the original one. This is with structuring element of 11. You start seeing that the individual circles started to basically be different, started to be a little bit, distinct. To be basically the connection between them became a little bit very thin. Okay. So basically, if you have an element, a structural element larger, basically here we used a structural element here of 25. We ended up with something that looks like this. Okay, you have apart from here, you actually see a number of objects here that is equal to exactly the same number of objects that are originally in the element, but actually they don't look like. Basically, don't look like the circle that we started up with. Okay, if we use a little bit larger one, basically everything here will be gone. Because basically, each time you're gonna lose a layer from these points. Basically, if you took a point here on the border, you have one element next to it that is 0, which makes it 0. When you apply the operation, you will make it 0. And the larger the kernel will be, the more elements inside that will have a 0 from the background in the kernel, which basically will result to basically a much faster erosion of this figure here. We can do it in a much nicer way actually if we move one step at a time. So for example, if I take, instead of doing this, if I just keep eroding one layer at a time. So if I have a structuring element here of 3, very small, okay? And much smaller at least than the ones that we had before, okay? And then I'm going to basically say that image one is equal to image, okay? And then I'm going to have a loop, say 10 times, okay? Inside this loop, I'm going to erode the same image by this smaller one, okay? Let's have it a little bit smaller. Let's have it like 5 and see what happens, okay? Okay, here I'm just applying the same kernel over and over again, okay? Instead of applying a large kernel once. Actually, you see that you can come up with something that looks very similar to what we saw before. So basically, if you apply it repeatedly, you will end up with something that looks still like this, okay? Let's try, maybe we can make it here like 10 times and see what happens. Actually, when you do it 10 times, you'd end up with something that looks like this. You have elements here that are basically, you see something that would kind of look like a circle, but not exactly like a circle. Let's try to make it a little bit smaller here, like just 7, for example, and see. Yeah, okay, you got something that is, you still have some connections here, so maybe 8 will work. It's okay, yeah, and it's, they look like much better circles, but actually you still have connections here, very small connections here you have to get rid of. So probably you have to do it a little bit more or like one more time here. Okay. So basically when you do that, you can very easily actually count something that looks like this. Now you have a number of objects here. Each one of these objects basically is represented here by only one blob. They call something that doesn't have a shape, they call it a blob. Okay, so basically if you want to count this, you can actually count the number of objects here, and you can come up with a very good estimate of the number of objects inside the image. This can be very useful in such applications as blood cell counting. You can basically, if you take a blood cell image, basically you're going to have like what they do in the lab. They have a slide that have many cells, many blood cells. Some of them are touching, some of them are separate. So basically you would like to end up with an estimate of the number of cells per square centimeter, for example. Okay, so that you can basically estimate the blood cell count based on this slide, for example. Okay, so you do it with things like that. Okay, so basically erosion can be very useful in separating objects that are touching. Okay, so it has, as I was saying, it has many applications, such as if you have if you want to count things and basically you want to separate things from each other. If you have binary image, if they are touching like this, the computer will consider them as one object. So basically, if you count how many objects you have in the image here, you will end up with 1. Here, you will end up with exactly the number of circles that were in the original. I'm not saying that these are circles. I'm not identifying circles. I would like to identify objects, because basically, if you talk about blood cells, for example, they don't look like circles. Basically, they can look like very separate, very different things from circles. But actually, the most important thing is to have an object corresponding to each cell, so that when you count these objects, you will end up with a good estimate or an accurate estimate for the number of cells in the slide. Okay? So do you understand the meaning of erosion and its application now? Do you have any questions about the erosion process? Okay. How about if we start with this same image and apply dilation? What do you expect to happen? What do you expect will happen when we do that here?
Maybe it will expand.
It will expand definitely, but is there any particular change in the image that would be very useful? Sometimes when you have gaps inside the image itself, sometimes you don't want them. So if you do dilation, these gaps will basically disappear. Okay, let's just apply them and see what happens. So we're gonna try exactly the same thing here. And basically we'll just use this figure only. And what I'm going to do is just replace image erode with image dilate. Actually, let's just try to change the sizes. These are too large actually, so maybe you can just make this 15 and this is like 21, something like that, so that we can see something useful. So I'm going to just do the same thing here and maybe display it in figure 2. So now see how it looks like. It almost basically the larger the kernel, the larger the outcome will be, and also the outcome will depend on the basically on the shape of the kernel itself. So if you use a circular kernel, it would look a little bit different here in the outcome in the border parts here. Okay, but see here, there's a difference. This is definitely larger. Okay. And basically, see, for example, this gap here became smaller here, okay, because this is the largest kernel. Okay, so when you end up with something that looks like this, you can actually identify the parts that are in the middle here. Okay, So basically, you can basically identify these parts in the middle and fill them out if you want to. Okay. So for the dilation process, basically all you have to do is just basically expand. Basically, if you stand in a point here, you put the kernel and basically select the maximum value within the kernel, and this will be the output. So if you have, if you imagine that you have your kernel here, then basically the maximum, as long as you have 1 point from the object, the maximum will be 1. So you end up with something that is much larger than the basically individual parts. Basically, it's going to join things that are close together. If you have gaps in the middle, they are going to disappear. Okay? You understand dilation? Do you understand what dilation does?
Yes, doctor. I understand.
Okay, there's a combined operation. I'm not going to talk about all the morphological operations, but I'm going to talk about a few of them that are very useful. There's a process called morphological opening and morphological closing. This is like a combined operation. This is like opening is like basically it's like